Hey everybody, it's Dr. Gilchrist, and as a reminder, I am not going to be in class tomorrow for a doctor's appointment that I have out of town, and so because of that, I wanted to make sure that I recorded a little bit of what we are going to be covering this week, talking a little bit about research fundamentals. So the last time that we were here on Thursday, we were starting to talk about statistical inference, and we were talking about sampling. And as you're going to learn throughout this semester, if we want to be able to estimate different confidence intervals, or if we want to do something like look at a t-statistic or do an ANOVA, if we want to do null hypothesis testing, statistical inference and its relationship to sampling is going to be pretty critical here. So I want to spend some time and first of all, I have a beverage, but I also want to talk about it. So, with that in mind, let's continue. So, to understand what's happening in a study, statistical inference is going to be really critical. And statistical inference is really nothing more than a set of different techniques to draw conclusions from a smaller sample to a larger population. Unfortunately, you are never going to be able to sample everybody in your population of interest, even at a very small college like Cadi. So inference is going to be critical. How does this differ from estimation, which you and I will be talking a lot about this semester? Estimation is just one type of statistical inference technique. Null hypothesis testing would be an example of another. So let's talk a little bit about how statistical inference is kind of supposed to work. So here we have a population, and as you can kind of see, this is a pretty small population. Most of the time, our population is going to be considerably bigger than this. We are obviously not going to be able to test everybody in the population because it is much, much bigger than this. Ideally, we are going to use some random sampling. Everybody in this population is going to have an equal opportunity of being selected for the sample. And ideally, if we're using random sampling and if our sample size is sufficiently large, what we're going to find is that the sample size is going to be representative of that population of interest. So a couple of other things that you need to know about populations. So your population has a mean. And whenever we're talking about things related to populations, we're going to use the term parameter. Statistics are always about samples. Populations have parameters. So if you need a quick little mnemonic, remember populations have parameters. They both start with a P. Our samples have statistics, and those are both with an S. And all of your parameters that we're going to talk about in the population, they are going to be in Greek. So as you can kind of see here, we have mu. Mu is the Greek symbol for the population parameter of our mean. So our population mean is mu. And 9 times out of 10, unless it's for this class where sometimes I will give you a population parameter for an exercise, you're not usually going to know what mu actually is. You're just not. You can't look at everybody. And because you can't look at everybody and you can't look at everyone in the entire population, you're not really going to know what mu is. So that's where statistical inference comes into play. We've randomly sampled the population. Our sample size ideally is going to be sufficiently large and representative of our sample size. And thus, our mean is going to be mu. So this M is our sample mean. That is our statistic. And we're actually going to calculate our mean from our sample data. And ideally, if we're using random sampling, if our sample size is sufficiently large, this sample should be representative of the population, and thus the sample mean, we are going to infer that our sample mean is our best estimate of mu. So a representative sample is going to be very useful for inferring population parameters. If your sample doesn't look anything like your population, your estimate is going to be off. And random sampling is always going to be the best thing that you can do to obtain a representative sample. Remember, it's more important how you select your sample than how many people are in your sample. I would much rather have 50 people who were randomly sampled than 100 who were selected on the basis of convenience. So random sampling is going to be ideal for statistical inference. As a refresher, with random sampling, every member of the population has an equal chance of being chosen or an equal probability of being chosen, and all members of the sample are chosen independently from one another. And random sampling is going to be the best way to obtain a representative sample, but remember that it's not a guarantee. Your sample size is also going to play a role in terms of the quality of your estimate. But statistical inference is always going to assume that data are from a random sample. Now, very briefly, last semester, I touched on the idea of what are called robust assumptions and what are called non-robust assumptions. If an assumption is robust, you can violate it and you can still do a statistical test. You just need to be very careful about how you draw that inference, and you want to couch your conclusions very carefully. Non-robust assumptions basically mean that if you violate them, non-robust kind of means that it's more fragile, it's not tough. And if you violate a non-robust assumption, you're not going to be able to do the test. Data coming from a random sample is a robust assumption. You can have data that's not from a random sample and still do a statistical test. You can still do a confidence interval, but you always want to be careful and note to others that your data did not come from a random sample. So what do you need for random sampling? Well, first of all, you're going to need a well-defined population. Excuse me while I move my head. So you need a clear idea of what your population of interest actually is. So this could be all students at Cotty. This could be all customers of a company, all registered voters. We don't necessarily want something vague like people. Additionally, you're going to need some sort of registry or list or a directory that is available to you to randomly select from. Now, in practice, a random sample may not be possible. So for example, when we talk about your population being people, which sometimes happens in cognitive psychology studies, unless we're looking at specific age groups or specific populations, our population is usually going to be people. And that means it's not going to be very well defined, and we're not going to have a really good random sample of the population. It's why we end up with those weird samples that usually come from college students in the Western Hemisphere. And additionally, even when things are well defined, a registry may not be available to you. So for example, when I was in graduate school and we were trying to recruit children for research studies, we previously had gotten a list of all children in the public schools, and we would randomly draw from that list. Eventually, over time, due to some unfortunate things that happened, that list was no longer made available to us. And so we had to come up with some different ways to try to get in touch with children, or rather with their parents for the study, to make sure that we got their approval from the parents first. And in those cases, that's when you have to potentially be creative. You look at public documents, things like tax records, property tax payments, and things like that. So registries may not always be available to you. Now, the alternative to random sampling is convenience sampling. And you and I both know that in our replication study, we are going to be doing a convenience sample. This is not a random sample. And because of that, when you're writing up your results in discussion section, you do have to make very clear that this was a convenience sample. And thus, the conclusions that we can draw from this replication are going to be a little bit limited. Now, many research studies are going to use convenience samples. Um, Getting data from college students who are currently enrolled in Psych 101 classes, those are great examples of a convenience sample. So, convenience samples are a lot easier to get. They are practically achievable from the population. They're a group of participants who are convenient to study. Remember that we call this a convenience sample. It is selected on the basis of convenience. It is not a convenient sample. And convenience samples are going to be very common in research, particularly in psychology. So that could be undergraduate students with a research participation option, ahem, kind of what we're doing here and kind of what I was brought up doing when I was in graduate school and in undergrad. We have passersby in a public area, advertisements, people who are in an area, and we're texting everybody to see how they feel about this political issue or that political issue, and things like that. So, what are some issues with convenience sampling? Well, like I kind of said, convenience sampling violates one of the major assumptions for statistical inference, and that's that your data came from a random sample. And like I said, you can still do statistical tests with a convenience sample. You can still run a confidence interval with a convenience sample. However, it's a robust assumption. It can be violated. And because of that, you have to be very careful when you're drawing conclusions. So, this is when your critical thinking skills really come into play. To what extent is the convenience sample that we have likely to be representative of the population of interest? And this is a case where potentially replicating with similar samples could be useful here. How representative are these samples? So, this is something, if you're doing a convenience sample, that you're always going to have to think about. So, for example, let's take a look at a few examples. So, let's say we have a survey of seniors, and we're looking at participants that are recruited from the gym and the dance hall of various senior centers. Now, some of you might think that this is pretty good, but I hope you notice, think about some different seniors that are in your life or older adults that are in your life. Are a lot of the older adults you know going to the gym or going to a community center? Maybe. But I know as many older adults who are content to stay at home or travel. And so it's possible that if we're doing a survey of older adults, if we're only looking at places for really active older adults, it might be very hard for us to get a sample that's representative of all older adults. If we're doing a personality survey, let's say that we're looking at participants who were recruited while passing by at a shopping center. And maybe this looks a little bit better to you, but I would question, let's think about the time of day. Let's think about the day of the week that it is. So, for example, if you're going to a shopping center in the morning, you might have people who have kids, or you might have older adults who are wanting to mall walk. If you go in the middle of the day, you might still see some of those people, but you're missing out on a lot of young adults and middle aged adults who might be working. If we're talking about a Saturday or a Sunday when most people do not work, we're probably going to get a more representative sample than if we get 10 o'clock on a Wednesday. And then finally, let's say we're doing a study of cognition. Participants were from a Psych 101 class at an elite university. And again, you already kind of know how I feel about samples of Psych 101 students. They're not representative, but they're a quick and easy way to get data. However, I want to really highlight elite universities. So, one of the things that we do find, if we're looking at data from places recruited from students at places like Harvard, Yale, Stanford, MIT, they're potentially going to look a little bit different than an example right behind me, my alma mater, Florida State University. Florida State is a public college with a higher acceptance rate, and there's going to be a lot more variability in cognitive abilities than if we're looking at a place like Harvard or Yale, which have really low acceptance rates, and even valedictorians are getting denied acceptance to those colleges. So we might have some differences between the different types of universities that we're talking about. And because of that, we might be dealing with two fundamentally different populations. So it's always to your benefit, especially if you're looking at schools that tend to have more of an Ivy League or an elite connotation. Be aware of their sampling practices. They might look very different. Those populations might look different than what you would see at a big public state university that may not necessarily be as prestigious. Although, of course, we know that some are. We have places like Michigan. We have a variety of different University of California schools. So again, be very aware of the populations that you're potentially dealing with. So now let's talk a little bit about experimental versus non-experimental research. So just as a reminder, all experiments are research studies, but not all research studies actually qualify as experiments. So let's do a quick overview of what is going to be needed for your research to technically be considered an experiment. So first of all, we need one or more variable that is being manipulated or being assigned by the researcher. This is going to be your independent variable. So for example, if I want to see if people's driving ability gets worse, if they text and drive, I put them in a driving simulator. Half of the group has to text while they use this simulator, and the other half doesn't. My manipulated variable, or the variable that I've assigned to different people, is whether or not they text. So that's going to be my independent variable. On the other hand, we can also have a dependent variable. That's the outcome that I'm trying to observe. So my independent variable is what I vary, and then the driving ability, based on whether or not people are texting, is going to function as my dependent variable. And because I am manipulating things, I can actually justify a cause-effect relationship. And additionally, by randomly assigning people to those different independent variable conditions, everybody has an equal chance of texting or not texting. I'm controlling for any individual differences that we might see. So maybe some people are better drivers, maybe some people are better texters, maybe we have people who are better at multitasking. We have good drivers. We have bad drivers. By doing random assignment and making sure everyone has an equal probability of being assigned to a particular condition, I ensure that those kind of individual differences are equated on both of my groups, and those differences will basically cancel out and my groups will be equivalent. So by this, I am potentially controlling for any of those confounds. We're going to describe this with cause-effect language. So we're going to have effects if we're talking about a verb. We're going to talk about effects if we're talking about a noun. You're going to hear things like produces, causes, makes. Now, what about non-experimental research? So here, we either have no manipulation of variables, maybe we're only measuring something and we're not assigning people to conditions. And because we're not manipulating anything, because we are only measuring, we cannot justify causal conclusions, and potentially we don't have the ability, through lack of random assignment, to rule out any of those confounds. So we're often going to describe this with association language. We can say they're related, we can say they're associated, we can say that they're correlated, but you're never going to hear us say cause-effect language. So here's an example of an experiment versus a non-experiment. So here's the difference between the two. So I want you to imagine that this wonderful beverage that I have here in my Stanley is NeuroAid. It's not actually NeuroAid. It's like some sort of strawberry mango drink mix from Walmart. But let's say NeuroAid has been reported to boost IQ, and I want to do some research studies to actually figure out if that's the case. So what would it look like if I were doing an experiment? What would it look like if I were doing a non-experiment? So if I were doing an experiment, I would have two different conditions. I would have a NeuroAid condition and I would have a water condition. And I would randomly assign people to those conditions. And then after drinking it for a certain period of time, I would then test their IQ. Now, in the case of the experiment, the type of drink is my independent variable. It's what I am manipulating. And then my dependent variable would function as IQ. Now, let's talk about a non-experiment. Maybe I don't have time to manipulate those variables. So I basically ask participants, how often do they drink NeuroAid, and also test for their IQ at the same time. So I'm not actually manipulating anything. I am only measuring. And what's kind of critical, notice that in the experiment, they drink NeuroAid and then I follow up and test their IQ. So the change in my independent variable comes before my dependent variable. In the case of the non-experiment, I'm asking for both of those things at the same time. So I can't tease apart which came first. And there's no manipulation here. So if I found that there was a relationship between NeuroAid and higher IQ, because I'm not manipulating anything, I have to say that NeuroAid use is associated with higher IQ. In the case of an experiment where I've actually manipulated that variable, I can say it increases IQ. Now, there could be some potential confounds in an experiment. Maybe NeuroAid is really expensive, and we also know that wealth or socioeconomic status potentially correlates with IQ. Access often leads to higher IQ. It could be a health issue. We don't know. Now, if we're doing random assignment and we have a sufficiently large number of people in each group, hopefully any confounds that we see in the experiment will be evened out and canceled out through that random assignment process. So now let's talk about measurement. We're going to talk about validity. We're going to talk about reliability, and we'll talk about the scales of measurement. I will probably stop when we begin to talk about the scales of measurement because I'd like to talk about that with everybody on Thursday in class. So sometimes what you and I want to measure is not something that we can measure directly. So for example, many of you know that I do a lot of work in memory and in attention. And something like short-term memory, especially in cognition, it's a theoretical construct. And it's used to describe behavior that we are actually observing. I cannot technically observe short-term memory happening with my eyes. I have to infer it through behavior that I see. So whenever we are looking at different types of things in psychology, like thirst or self-esteem or intelligence, or an example that we're going to run through a lot in this section is a concept that comes up in industrial organizational psychology, job satisfaction. So a construct is going to be the abstract concept that we're interested in. And from that construct, we are going to develop what is called an operational definition. So operational definitions are very precise procedures for actually measuring values that represent a concept. So for example, if we're interested in self-esteem, we're going to talk about a score on a self-esteem test or inventory. If we're talking about something like job satisfaction, we might ask somebody, how much do you like your job on a scale of 1 to 10? If we're talking about short-term memory, we may have people listen to short lists of digits and then immediately have them report them back in the order that they heard them. So we have these different ways that we can measure values that really hit on that abstract construct that's hard for us to actually physically measure. And then we have the measured variable. This is going to be the actual variable that you're measuring. So here's kind of an example. So we have two different theoretical constructs that we might see in something like IOPsych. Job satisfaction, which is basically how much do you like your job? And then we have job performance. This is how good are you at your job? And as many of you know, you may like your job, but you may not perform very well on it, and you may perform very well at your job, and you may not like it very much. So these aren't necessarily very highly correlated. They can be highly correlated, but they don't mean the same thing. So let's kind of go through a couple of examples. So let's start with job performance. So we're going to take as an operational definition of job performance, let's say monthly sales. So we're going to measure sales and take that as an index of job performance. So job performance is basically going to have this very clear definition of the sum of the participants' monthly sales. So this is going to be the operational definition for job performance. And this is how we can take something very theoretical and hard to observe and actually put it into a behavioral measurable variable that we can actually see. Now, let's take something like job satisfaction. So job satisfaction, how much do you like your job? We give them a survey with a Likert scale. I know it's technically Likert, but I'm still going to call it Likert. And the higher the number, the more they like their job. So your operational definition is functioning as a stand-in for that ultimate construct or concept of interest. Now, another thing to note is that you can measure variables in a variety of different ways. This is not the only way to measure job performance. This is not the only way to measure job satisfaction. So the same variable can be thought of and operationalized in a lot of different ways. But one thing that's really important, the measured variable should be reliable and it should be valid. So for example, another way to operationalize job performance could be customer ratings or supervisor ratings. And ideally, if these are all good measures of job performance, these should all be relatively highly correlated with each other. So if we want a measure that is reliable, reliable here basically means repeatable. Like every time that we repeat the measurement, we're going to get a pretty similar result. We're not necessarily going to get the exact same result, but we're going to hit on something good. So if somebody is good at their job, they may have a good month or a bad month, but generally those customer ratings are going to be pretty consistent over time. And if we're talking about something that's valid, we mean something that is accurate and it's true and it's measuring what it's meant to measure. So maybe we have somebody who is really attractive. They're not very good at their job, but because they're attractive, they get really high customer ratings, even though their supervisor ratings are not great, their sales ratings are not great, but their customer rating is really good because, well, people like looking at them. In this case, this would not be a very valid measure of job performance. Now, let's say that we looked from data on customer ratings over multiple weeks. So if this is a reliable measure, scores should be similar across the same employees. If they're reliable, they should have similar ratings from week to week. And one of the ways that we can kind of look at this, if we're looking at something like IQ or self-esteem or depression, we can look at what is called test-retest reliability. We can look at how similar results are when the same participants are tested in the same way on two different points in time. So let's talk a little bit more about measurement. So let's say we have a measure of job performance, and we have customer rating, and we have monthly sales. Here are our definitions of reliable and valid, which I have just shown you. Now, if they're valid, the same employees should have pretty similar scores for a lot of different ways of measuring performance. So the customer rating should be accurate and should be a true reflection of job performance. And when we see multiple measures hitting on the same result, this is what is referred to as convergent validity or converging validity. Basically, here we're looking at how similar results are when we're measuring participants with different operationalized measures of that particular construct of interest. And we'll talk a little bit more about some of the different ways that we can quantify both reliability and validity when we talk about correlations. So I'm going to go ahead and stop here. This is our scales of measurement section. I will talk more about this on Thursday. We will also have our quiz on Thursday. We'll take our first scratch off quiz. So you see, I've got them right here. I am ready to go. Make sure to bring your coins, and I will see you all on Thursday. Have a great Tuesday. Bye, everybody.